Hello.
Hi, do you hear me?
Yes.
Okay, cool. There was some issue with microphone. But nice to see you. How are you doing?
I'm fine. Um,
Mm,
I was a little bit behind program that was defined initially, so now I'm currently read everything, and I'm here. I
okay,
read
that's cool.
magnetic fields chapter 11.4 and 11.5, and I'm here
Mhm,
to listen what you have to say. Basically, deepen my knowledge.
sure. Yeah, so by the way, if you, because of some reasons, were behind the lacking behind the course, all lectures are recorded and you can watch them on this Google folder, which is shared between students. By the way, there are recorded lectures, not only mine, but also recorded lectures from all uh, professors who are delivering lectures on this course, Physics 162, during this year. And that's why could be also useful for asynchronic learning experience.
Thank you. I'll watch that as well.
Mhm. Okay, let's wait for another minute. Maybe someone else will join. So, as uh, you may remember from the last lecture, we uh, introduced the magnetic field, uh, which is some form of matter that exists in the space around moving electric charges. So this is one of the key difference between magnetic field and electric field, because electric field always exists around charges, regardless of their stationary or moving conditions. Magnetic field only is created by moving charges, and also in the contrary, it is acting on moving charges. So there is some magnetic force exerted on magnetic charges, and this force is defined by the like three quantities, which is electric charge, um, its velocity, like vector product of velocity vector and magnetic field vector, B. So we measure magnetic field in Tesla. It's a unit for measuring the strength of magnetic field in the point of space. And also we discussed how particles are moving in, like charged particles, are moving in uniform magnetic field. So we had some quantitative description of this type of movement, including taking into account the exerted magnetic force on these moving particles. Today we will continue working with magnetic field, its interaction with moving charges, but we will focus on charges which are moving in a conductor. So it will be conductor which carries some electric current. Obviously, we have some moving charges inside this conductor. They have some directional speed, which is called, like we can call it velocity also, would be considered treated as a vector. It's a so-called drift velocity. And obviously we have some internal electric field inside this conductor, because that is the driving force to move these charges with this drift velocity in certain direction. And of course, there will be some effect from the side of uniform magnetic field on such charges. So there will be exerted certain magnetic force on them. At the same time, since they are constrained in the conductor, they cannot be be taken out from the conductor. This force will be automatically exerted on the conductor itself. And each segment of the, for instance, a wire with running current through it will experience certain influence from the side of uniform magnetic field around it. And today we are going to understand what exactly is going on and quantitatively explain this type of interaction. Okay, let us change the camera. And so we know that there is some magnetic field, magnetic force exerted on a moving charge. And that can be described by this equation. So there is some magnetic force equal to electric charge. So now we consider positive electric charge, but keep in mind that it matters because we use positive or and negative electric charges that will define different directions for the magnetic field. So now we consider positive electric charge, and then it's product of some velocity vector, change, and magnetic field vector. So we know this for a single charge, but in the conductor, when there is some electric current flowing through it, there is a continuum of electric charges. So this system of electric charges contains much more than just one. So we need to take this into account and also take into account that all of them are moving with this drift velocity. So in that case, we can write that total magnetic force will be equal like force which is applied to one electric charge moving in the conductor, and then we need to multiply it to the number of electric charges which are in the unit, which are in the volume of the segment which we consider, of this segment of the conductor which we consider. And in order to make it more general, we will just use it per unit length. So we will operate with concentration of charge carriers in the conductor times area, the cross section of the conductor, and times length of the segment. So this product area and length will give us volume, and that's why we will have concentration, means number of charges per unit volume. So when we multiply volume on charge concentration, we just get some total number of charge carriers which are in this segment of conductor. And that will give us total magnetic force which is exerted on this conductor. So we know from previous lectures when we considered electric current that it can be written as follows, that N times Q times V D times area. So this is this would be electric current density. And if we multiply electric current density by the area of the cross section, we get the current. And that's why, taking this into account, we can rewrite this equation for total magnetic force exerted on a conductor with flowing electric current. So we can write here the magnitude of electric current times L vector multiply B vector. And this L vector is the vector which points the direction of the electric current, and its like magnitude is equal to the length of the segment of the conductor. So if we have some not straight conductor in magnetic field, let's say we have a magnetic field and some random shape conductor with electric current, then it's necessary to consider small segments of this conductor, and they will be represented with ds vector. So this is small length of the small segment of this conductor, and also direction is defined by the direction of electric current in within this segment. So that's why we can write for very small magnetic force which acts on this small segment of the conductor as I times ds multiply like some vector product with B vector. So in this case, also just a reminder from previous lecture, since we have here a vector product, that this small force, like magnetic force, will be perpendicular to the plane formed by these two vectors, ds and magnetic field vector. So now we can write the equation which will help us to, in general case, to determine the magnetic force acting on a conductor with electric current. So in this, to do this, so it's already quite obvious, we need to integrate along the length of the this random shape conductor, which consists of many of these small segments. Sorry. So let's say we have point A here and point B. So if we want to know total magnetic force exerted on this conductor, from point B, A to point B, then we will have some integral. So it's I times integral. I is constant. It's the same in any cross section of the conductor, and it originates from the law of conservation of electric charge. We don't lose charges from the side walls of the conductor. That's why in each cross section along the conductor, we will have the same electric current. Regardless, by the way, even if we have different cross section area, so it will change, or we will have some different materials properties, it doesn't matter, it will be always the same electric current through each cross section. So here will be integral from A to B of vector product ds times dB. Sorry, not dB. It's just B. We have uniform magnetic field. Okay, so now once we already have this general equation, let us try to apply this to some case and see how it works. So let us consider a wire bended in the form of some semicircle and placed in external magnetic field. So this is our magnetic field. Then we have such loop, so it's closed loop in the form of semicircle. So here we have our system of coordinates, will be x, y. Then we have electric current flowing in this direction, like it will be flowing like counter clockwise. And also it will flow here, like this. So this semi-circle will possess some radius. This is radius r. And maybe we will define this a bit later, the segments delta S for this curved part of the loop. But first, let us consider the first segment, which is straight line. So again, we have 2 points like A and point B. And here is 0 for X. So the coordinate of point A will be minus R divided by 2. And for coordinate for point B will be R divided by
2. Can I ask why? Because isn't it just R? Because it's radius. You start from the origin and then go to B. Same radius.
Yeah, sure. You are right. We'll need to. Yeah, sorry. We need to go for R. I already. Yes, it's minus we have here. So it will be, since it's in the center and we have radius, it will be from minus R to R. Yeah, thank you very much. So with these statements, we can proceed further for calculation of the force which acts on the segment 1. So let's call this straight segment 1, and this curved segment will be 2. And then we can calculate later force for segment 2. So magnetic force on segment 1 will be current. Then again, we can rewrite this equation which we derived on the previous slide. It will be from point A to point B, ds vector product with magnetic field vector. Then it will be equal to electric current integral from minus r to r, which corresponds to coordinates of these points. And then it's straight and perpendicular to the direction of magnetic field. So that's why it will be sinus of 90 degrees of this vector product. So we have unity and our direction. We need to define in which direction it will go. So if, as we discussed during last lecture, if we point our forefingers of the left palm in the direction of electric current, and magnetic field vector will go into our palm, then the straight sum will show us the direction of the magnetic force. So in this case, it will be perpendicular to the plane of the image in our direction towards us. So we will consider that this is axis Z, this positive direction for axis Z. And in this case, if we take this all into account, it will be here magnetic field times dx. It's the change of the coordinate within the axis x. And then we need to multiply it by unit vector k, which will define the direction. And since it's unit vector along the axis z, so it will define direction from the plane of the image towards us. So now it will be equal current and magnetic field strengths. These are constants. And here is integral from minus r to r and times dx. So this will be equal to, oh, sorry, once more, I forgot this k vector, unit vector. And this will be equal to I times b times k vector will be r minus r, and this is equal to 2 times I times b times r and our unit vector, which defines the direction of this force. So this force will be defined by the magnitude of electric current, by the magnetic field vector magnitude, and by the distance, actually, because 2 times r, it will be distance, total length of this segment from point A to point B. Okay, so with this segment, we are done. And let us proceed further with the segment number 2. So in this case, since it's semicircle, it's very convenient to deal in polar with this in polar system of coordinates. So here we can define some angle theta, like position of this radius r. And here, maybe I can change the color. We have some vector ds, a small segment of this arc. And this can be represented where d theta, like small change of the angle theta. In this case, we can write for the force, magnetic force acting on the segment 2. Actually, not on the segment 2, but on this small segment, which we defined as delta S. It will be electric current times delta S vector product with magnetic field vector. And this will be, now it will be I times B times sinus theta times ds, and we need to define the direction. So this should be somehow separated. Now we need to define the direction. So let us see what will be the direction of the magnetic force if we direct our 4 fingers of the left palm in the direction of current through this segment 2, and then magnetic field will go into our palm, then we see that the sum will show us direction opposite from the previous direction. It will be along axis z, but in opposite direction. So it will go from the plane of the image from us. And in this case, we need to put vector, unit vector k, and put here minus to highlight that it will go in the opposite direction from the direction of axis z. Okay, so we have this part, and now we can integrate it in order to get the total magnetic force acting on this second segment of the loop. So it will be F2 equals to minus integral. So again, how do we define point this? If we want to go through whole semicircle, and in order to do this, we need to go from 0 to pi, which is 180 degrees or pi radians. Then we have product of electric current. Another thing which we need to define before writing the final expression. We have still here ds, and we need to express this ds in terms of radius and angle theta. So ds, let's write it here, will be equal to radius times d theta. So it's small change. The length of this segment will be equal to the product of radius of the curvature and small change of the angle theta in radians. So once we take this into account, then we can write instead of ds, its expression r times delta theta, and eventually we get I times r times b times sinus theta times d theta, and this unit vector k along the axis z, but we have this minus, so it shows that it goes in perpendicular to the plane of the image, but in the direction from us. So now we have constants out from this integral, and this k unit vector integral from 0 to pi sinus theta d theta. Let's go to another slide. So it will be minus current B RB times RK vector. And this integral will be minus cosine theta from 0 to pi. So this minus and this minus cancel out each other. Then we have I times B times R cosine pi minus cosine 0 times k vector. And this is equal. So here we have minus unity, here we have unity. So in total we get minus 2i times r times b times k vector. So we see, so we got for both forces F1 and F2 the same equation, expression. However, the difference is only in the sign. So we can write that the vector sum of two forces, magnetic forces acting on two parts of this loop, are equal to 0. So means that there is no net force acting on closed, like on the conductor, which is in the form of a closed loop. When we consider like this closed loop of electric current flowing through this conductor, by adding magnetic forces acting on different segments of this loop, we will get 0 eventually, which means that there is no net magnetic force on a closed loop electric current. Another thing which comes out from here, and we need to highlight this, is that the magnitude of magnetic force is the same on conductors with the same electric current between 2 points like A and B, regardless on the shape of this conductor. So it could be straight line, as we had in this example, segment 1 of the loop, or it could be curved in any form conductor, but still ends and of this conductor are in the same points A and B. The total magnetic force acting on these different shaped conductors will be the same. And that's why any loop of any arbitrary shape will result in satisfaction of this condition. So total net magnetic force on closed loop will be equal to 0. So it is true about total force, but if we consider a closed loop in magnetic field, there could be not not equal to zero net torque on this loop. And that is very important feature create when magnetic force creates a certain torque around some axis passing through the loop with electric field, because this finds really very broad practical application in electric actuators like motors, and maybe later we'll discuss once more quite important application of this feature. But definitely there are like many. However, the most important is this conversion of mechanical work, conversion of electric energy, which generates current and magnetic field into mechanical energy. So now let us consider some this torque which is created on current loop in uniform magnetic field, and try to quantify this. So the system which we will consider will look something like this. So this is our magnetic field, uniform magnetic field. Then we have a rectangular loop with current I. So let us consider that this current is flowing counterclockwise. This is I, and give names like numbers to each of these segments. It will be 1, 2, 3, and 4. So length of this rectangular will be A, and width of this rectangular will be B. So segments 1 and 3, they are parallel to magnetic field vector in this given position. So we imagine how it's aligned. This plane of this loop is parallel to the plane of the image, and sides 1 and 2, 1 and 3 are parallel to the magnetic field vector. In this case, magnetic force will be equal to 0 because there is no angle between this, the direction of the current flowing through these segments and magnetic field vector. So we don't consider these forces, but there are segments 2 and 4 which where electric current flow perpendicularly to the magnetic field vector, and definitely there will be some magnetic forces acting on these segments. So we will call them F2 and F4. So by magnitude of these forces, they will be equal, and this will be equal to the product of electric current, length of these sides, A times B, strength of the magnetic field. Now let us consider the look from bottom, like projection, but from the bottom side of this loop. So it will be here, current will flow towards us, this current. So we are looking at these points from the bottom. So here it will flow towards us, and here it will flow from us in the plane. So now if we consider point O, which is in the middle of this side of the loop, and define where will be the what will be the direction of magnetic force, we will see that this is our force F2, and here is force F4. Distance between this point O, with respect to which we will calculate the torque, is B divided by 2. So apparently I was confused with this example previously when I was writing R divided by 2. So now we know the distance between the points where magnetic forces are exerted to the point O, where with respect to which we are going to calculate the torque. So we can calculate the torque. It will be F2 times B divided by 2 plus F4 times B divided by 2. And we know the magnitudes. It will be I times A times B times sum of these distances. And eventually we get I times A times B times magnetic field. And this is nothing else as the area of this loop. So we can write that I times A times B. So the torque with respect to the point O will be determined as the product of electric current flowing through this loop, its area, and strength of magnetic field. So let's go further. And it's necessary to underline that this torque which we calculated, like current times A times B, is the maximum torque which can be exerted on this frame with respect to the axis which goes through the point O. Because we have special alignment of this frame parallel to the, so this the two sides of this frame of this loop, in particular side 1 and 3, they are parallel to the vector of magnetic field B. And in general, there will be some angle if we have any possible orientation of this loop with respect to magnetic field. And let us consider this case. So again, we look kind of projection from the bottom. Let's have some random orientation of this loop. So here we have current which flows towards us here we have current which flows from us. And we have also the same direction of magnetic field. So here will be some angle theta. It's how our frame is tilted with respect to vertical direction. And this is vector A. We will define this vector a bit later. And it's also angle theta. So it shows how the vector A, which defined by the properties of this loop, is oriented with respect to the direction of magnetic field vector B. So we have the same forces, F2 and F3, F4, acting on these parts of the loop. And this distance from point O, like perpendicular to the line which goes through the vector of the force 2, will be B divided by 2 times sinus theta. So it will be already smaller. So the shoulder of this force F2 with respect to point O will be smaller. It was, when it aligned parallel to the magnetic field, it was B divided by 2, and now it will be B divided by 2 times sinus this angle theta. And of course, torque will be smaller. So in general, we can write that it will be I times A times B. And here will be B divided by 2 sinus theta. And again, plus the same B divided by 2 times sinus theta. So we will get I times AB times magnetic field times sinus theta. And this is equal to I times A times B, this maximum torque, which can be exerted on the frame on this loop times sinus theta. And from since we have this sinus here, we can represent in general the torque as a vector quantity as I, the scalar quantity of electric current, times A vector times B vector, magnetic field vector. So this, as I mentioned earlier, we need to define this vector A, what it is. So vector A is always perpendicular to the plane of the loop, and its magnitude is equal, so its absolute value is equal to the area of the loop. So, but in order to define this direction, we can use this rule of the right sum. 1 second, I will share my screen. Yeah, so if we curl our 4 fingers in the direction of electric current in the loop, then of our right hand. Then this sum will show us the direction of vector A. So it always perpendicular to the plane of the loop. Its magnitude is the area of the loop, and its direction, specific direction with respect to the loop, will be defined by the direction of electric current flowing in this loop. If it changes to clockwise direction, then of course this vector A will be directed downwards. Okay. There is another vector mu. We will just discuss this right now and introduce this also. So they have the same direction as both vector mu and vector A have the same directions, and they are their directions are defined with the same approach. So now the product of this current and vector A can be called as a magnetic dipole moment, and it is written as mu. So this mu is magnetic dipole moment equal to the product of magnitude of electric current and vector A. And units for this magnetic dipole moment are ampere times square meter. So if, for instance, we have not just one loop, but some coil with many loops, let's say n loops, then this magnetic dipole moment can be given as follows. So let's say it's mu of coil with n loops. So we just multiply the magnetic dipole moment of a single loop, I times vector A, by number of loops. So this is the way how we can determine magnetic dipole moment of a coil. And therefore we can express the torque exerted on this loop as the product, or maybe also coil, which consists of many loops, will be as product of two vectors. It's magnetic dipole moment times magnetic field vector. So in analogy to the electric dipole, when we consider some potential energy of electric dipole and electric field system, we have shown that it will be potential energy equals to minus of scalar product or dot product of this electric dipole moment to electric field vector. And that is also true for the system of magnetic dipole moment and magnetic field. So we can write that potential energy of such system will be equal to minus mu vector dot product with magnetic field vector. So since this product of magnetic dipole moment with magnetic field vector define the torque, that is really very important feature, because as I mentioned, it is widely used to convert electric energy into mechanical. So they have found very broad practical application in electrical motors. And but besides that, there could be some other applications. And for instance, one is measuring the strength of like the magnitude of electric current, so in so-called ampere meters. And the way how it works there is some permanent magnet and a coil made of several loops of electric wire, which is around this permanent magnet, but can rotate around it. So it's fixed in 2 points and can rotate about some axis, which is going, and this permanent magnet is located inside this coil in order to create uniform magnetic field around it. So once we have some electric current when we measure, so this electric current flows through this coil around permanent magnet, and obviously there is some magnetic force acting on the parts of this loop, resulting in some torque. And this torque will be proportional to the magnitude of electric current. So we see here that this torque is proportional to electric current. Area and magnetic field are constant, they are not changing. And that's why if we attach some string to this coil, it will deflect from the steady state position proportionally to the current which flows through this coil. And if we attach some needle to this coil and have some calibrated display behind this needle, we can get the from reading the where this needle is showing and how much the coil is deflecting from this its equilibrium condition. We can determine the magnitude of electric current. So this is the mechanism of very straightforward ampere meters, which can show us the magnitude of electric current in different electric circuits. The resistance of this coil is very small and can be neglected with the resistance of electric circuit. And that's why there will be minimum voltage drop over this measuring equipment, this ampere meter. So it will give us quite accurate results in measuring magnitude of electric current. And obviously it directly applies the interaction of magnetic field and conductor with electric current, which we discussed during this lecture. Okay, so we are running out of time, actually a bit more already than necessary. Thank you very much for attention. If you have any questions, you're welcome.
No, it's all was clear.
Thank you for attention. Then we will meet on Friday. And there we will consider one of very important application of interaction of moving electric charges and external uniform magnetic field. It's so-called Hall effect. And this is just nice physics behind of this Hall effect itself, but it also found very broad practical application in engineering, like in so-called Hall sensors. And also it is very powerful technique for measuring properties of semiconductors or just conductors. So we will consider both cases. Hopefully we will have enough time since it's quite close to my field of research. So I'm working in the field of physics of semiconductors and semiconductor devices. And Hall effect is quite often used in experimental measurements during our research in the labs. So that would be interesting topic for application of this type of interaction between moving charges and constant uniform magnetic field. Okay, then hope to see you on Friday and have a good day. Bye-bye.
Thank you very much. Goodbye.
Thank you. Goodbye.